In lesson 9.2, we're going to talk about the binomial theorem. This is going to relate a lot to combinations, which we talked about in the last lesson. The focus of this lesson, we're going to talk about powers of binomials. Remember, a binomial means two terms. So a polynomial that has two terms is a binomial. Pascal's triangle, which we've talked about in the past. The binomial theorem, that will be new. And then we're going to talk about factorial identities, which we talked about in lesson 9.1 as well. The power of a binomial is basically referring to if we have two terms, in this case a plus b, and we're raising that whole quantity to some power n, where n is going to be a whole number. So starting from 0, increasing by positive integers, 1, 2, 3, 4, and 5, and so on. Okay, that's going to continue. If we're looking at the powers of these binomials, there starts to be a pattern relating to what happens to the exponents and what happens with the coefficients. So let's just say we focus on x plus b to the third power. Notice our coefficients in front of each term, 1, 3, 3, and 1. And then if we want to focus on the a value, the exponent starts with 3, then it decreases by 1 each time, so it becomes 2, 1, and then 0. If we look at the exponent on b, it starts as 0 and then increases by 1 each time. So if we look at each term in here, 3 plus 0 will give us our exponent of 3 that we started with, 2 plus 1 gives us 3, and that pattern continues on. So if you add the exponents on each term, they always have to have a sum equaling the total that we started with. Okay? And some of these values should look familiar to you from our discussions with Pascal's triangle in the past. Now we're going to discuss where those coefficients in front of each term comes from in Pascal's triangle. Okay, so first we need to understand that those values are relating to combinations. Okay, we talked about combinations in the last lesson. NCR, N referring to our total objects, R referring to how many we're choosing out of that total. Another notation to stand for a combination is NR. Okay, within those parentheses, when you see that notation, immediately understand that we're talking about a combination. Okay, that's often used if we're talking about binomial coefficients relating to the binomial theorem, which we'll talk about later. Okay? So, if we focus on Pascal's triangle on the left, we can relate each of those values on the left to a combination on the right. For instance, the first one in Pascal's triangle, remember this is row 0, which we start with, is going to be 0 objects, and we're picking 0 out of 0 objects. There's only one way to choose 0 objects from nothing. Okay, so that's where that one comes from. Now let's look at this first value in row 1. If we compare that over here, if we're taking one object and we're choosing 0 from that, there's only one way to choose 0 from 1. You just take nothing. That's where that 1 comes from. If we skip down and look at this 3, relating it to this combination over on the right, we have 3 total objects and we're choosing 1. There's 3 different ways I can accomplish that. I can pick the first number, second, or the third object. So that is where that value of 3 comes from. If we're relating over here, we'll look at one more example, to this 1 starting at the beginning. Okay, going down to the 4th row, 4 total objects, again taking 0 from there. There's only one possible way to pick nothing out of a group of 4, so that is where those values are coming from. So usually it's a lot easier to just remember these values in terms of Pascal's triangle, but we need to have an appreciation of where these values come from, so that's why we're going to discuss these combinations on the right. They show us where the values for Pascal's triangle come from. Here's our first look at the binomial theorem. Okay, we can use this theorem to expand binomials raised to positive integers. it's honestly easier to just use Pascal's triangle, where we can identify the coefficients quickly and recognize that pattern. But this is something you may see in a college algebra class or calculus moving on in your mathematics. So I want to give you a decent background of what this theorem says and allows us to do, so that when you see it later, you know what the heck they're talking about. Okay, so if we're raising a binomial a plus b raised to the n power, and we're going to expand it, remember this notation, n choose 0, that's standing for the combination. Notice our exponent, which was n, is in the top for all of our combinations. Across the bottom, we start with 0 and then increase by 1 each time until we get to n, our total number of objects. Okay, so that's how we're relating combinations to the coefficients out in front. For our exponent values on a, we start with n, and then we will decrease by 1 each time. For the exponent values on b, we start with 0, and those exponents will increase by 1 each time. Before we start expanding binomials, we're going to compute the coefficient for a given term of a binomial. So in this example, we have x plus 2 raised to the 15th power. We want to find the coefficient that would be in front of the x raised to the 10th power. Okay? So first thing we have to do is set up our combination. We have 15 objects, and we're going to choose 10, which is the exponent value on this term, x to the 10th power. We have to multiply that by 2 to the 5th power times x to the 10th power. Okay? We know that's going to be 2 to the 5th power because if we're looking for the x to the 10th power term, we know if we add those two exponents, 5 and 10, they have to equal our total, which is 15. So now 15 choose 10, that combination is equal to 3003 times 2 to the 5th is 32 times x to the 10th, which, if we simplify that out, is 96,096 times x to the 10th power. So our coefficient would be the 96,096 in front of our x to the 10th term in that binomial expansion. So we want to expand the binomial expression a plus b raised to the 4th power. Okay, so this is going to be the 4th row of Pascal's triangle. So our coefficients will be 1, 4, 6, 4, 1. If you don't know where those values came from, you need to pause and go back and look at Pascal's triangle and figure out where those values came from. Okay, so those stand for the coefficients that are going to be in front of each of our terms. So if we're expanding a plus b raised to the 4th power, starting our first coefficient is 1 times a raised to the 4th power times b to the 0 power, plus, now we're going to our second term, coefficient of 4 times a, exponent is going to decrease by 1, will be to the 3rd, b, exponent will increase by 1, plus 6 times a, again our exponent will decrease by 1 on a, exponent on b is going to increase by 1, so that'll be 2, plus 4 times a to the 1st, b to the 3rd, plus 1 times a to the 0, b to the 4th. Okay, so now we just have to go through and simplify each of these. The first term, b to the 0, anything raised to the 0 power is 1, so all we have is a to the 4th. Second term, we have plus 4 times a cubed times b, plus, we look, we have 6a squared, b squared, nothing simplifies there. Next term, we have plus 4 times ab cubed. Nothing simplifies there. And the last term, a to the 0 is 1, so we're just left with b to the 4th. So that's how we can apply Pascal's triangle to expand a binomial. Okay, that's basically using the concept of the binomial theorem and that coefficient triangle. All of that relates to Pascal's triangle. Here's another example of expanding a binomial. In this case, we wanted to expand z plus 5x squared, all of that raised to the 5th power. So we're going to be in 5th row of Pascal's triangle. The coefficients will be 1, 5, 10, 10, 5, and 1. I've already gone through all the steps. In order to expand this, you need to go through and see where all of these values came from, how I use parentheses, and you're going to see why parentheses are very important in this case, and how I simplified to get a result on the bottom. Okay, so you can go through that and see where all those values came from and figure out what I did. Last thing we're going to briefly talk about is the basic factorial identities. So for any integer where n is greater than or equal to 1, n factorial is equal to n times n minus 1 factorial. So all that's saying is if we had 7 factorial, that's equal to 7 times 6 factorial, which is pretty straightforward because 7 factorial, we're taking 7 times 6 times 5 all the way down to 1. On the right side, we're taking 7 times 6 factorial, would just be 6 times 5 times 4 times 3. So that's really straightforward, saying the exact same thing. The second one, for any integer n greater than or equal to 0, n plus 1 factorial is going to be equal to n plus 1 times n factorial. So if we want to look at an example of this one, that would be the same as 8 plus 1 factorial equal to 8 plus 1 times 8 factorial. Well, if we simplified this, 8 plus 1, this would be the same as 9 factorial equal to 9 times 8 factorial. So this is saying the same thing that that first property just said. Okay? So 2 basic factorial identities, not too complicated. The main focus of this lesson was relating combinations to the values in Pascal's triangle and using those values to expand binomials.